Okay, hi everybody, let's get started. So first of all, let me mention, in case you haven't noticed, the midterm exam is on Monday next week, so a week from today. We'll post a practice exam in the next few days, by Thursday night, let's say. A practice exam and the solutions. It will give you some idea of the format of the practice exam. Most likely it will be just a few short questions, maybe 2 or 3 slightly longer questions. So the whole thing is 80 minutes. It won't be very long. And there's no materials allowed in the exam whatsoever. So no cheat sheet, no nothing. Okay, so today we'll talk about learning theory. You know, it's a very general title. Really, it'll be just the tip of the iceberg in certain things on learning theory, which is a huge area within machine learning. Specifically, I want to talk about the probably approximately correct model. Now, this lecture, I guess I've taught it in several courses by now. And I often like, in courses where there is a final exam, I like to have a vote where people get to decide which topic to vote off the final exam. So this topic is often one of the leading contenders for getting kicked out of the final exam. And I've often seen, when there's this vote, and then people on Piazza say, oh, you're crazy, this topic was one of the most interesting. So I think the issue is, to me, it seems like a really beautiful topic, some really great insights that we'll see today if you haven't seen this stuff before. On the other hand, it's a relatively difficult topic, especially in terms of the definitions. So what makes the definition hard is when there are many quantifiers. And here we'll see definitions with 3 quantifiers, for all, exists, for all, stuff like that. So definitely the definitions are pretty hard to digest. And I'll try to go slowly and sort of give you some polls to help you think about them. But it's definitely a challenging topic, and yet I think a very rewarding one if you really make the effort of understanding some of the insights behind the definitions and the results. Okay, so with that, let's start from the beginning and talk about the probably approximately correct model. Can you just raise your hand out of curiosity if you've already seen this topic before? Okay, good. So just a few of you. So this will be new to almost everybody. Can you raise your hand if you've seen the definition of VC dimension before? Okay, same people basically. Cool. Okay. So this model, PAC, probably approximately correct, is due to Leslie Valiant of Harvard University. It was introduced in 1984, and it's one of the contributions that underlie his Turing Award. So the idea is that, to be able to formalize the idea of generalization, right? So we know that a learner can do well on a training set, but can do badly in general on the original distribution or in the real world. So Zico talked about some of these phenomena last time, things like overfitting, and we'll get back to these real-world connections at the end of the lecture. But really what we're trying to do here is, in a very clean and abstract way, capture the idea of when we can guarantee that learning on a sample, on a training set, is going to generalize well, is going to give us good results in the real world on some general distribution. So that's what we're trying to capture here. And here is the I think, really ingenious formal model that Valiant introduced. So, there's going to be quite a few notations, quite a few, like I said, non-trivial definitions. We'll try to go over this slowly, but please, stop me if you miss anything. So we're going to have an input space X, which is the space where our basically data lives, where our examples live. And we're going to have a fixed distribution denoted by capital D over X, over our input space. So this distribution is unknown to us. Essentially, we're going to get examples drawn from this distribution. And we're going to try to do well with respect to this distribution, even though we don't know what it is. But the important thing is it's going to be fixed throughout the learning process. Now, we, the learning algorithm, are going to receive a set S of M examples, or M instances, x1 to xm. So these are M points from the input space that are sampled independently according to the distribution D. Right, so this is basically the data that we see, the data set that we see, and it's going to be sampled from this fixed distribution D. Now, we also have a function class, capital F, of functions that map the input space to plus or minus. So we're going to focus for almost all of the lecture. I'll just mention at the end something else, but we'll focus on classification. So we think of functions that take every point in the input space and assign it a label. It's either a positive example or a negative example. And our function class is called capital F. Now, the next point is an important point that actually makes a big difference. We're going to assume a target function that we denote by f sub t, and it's a function in our function class. And this is sort of a big assumption. We're basically going to assume that the truth is some function in our function class, and that's what we're trying to learn. So this is, some people call it the realizable case. There are some differences between this case and the case where there is no function that sort of perfectly labels the data. And I'll touch on the differences towards the end. But really, for the whole lecture, we're going to assume that there is a target function, f sub t. And then the training examples, it's going to be a set z. So it denotes of the input points, the xi's that we sample from our distribution. And for each one of them, we have its true label, f sub t of xi. Right? So we said f sub t is like the target function, the truth that we're trying to learn. And what we're getting is, for each one of the m points that we sampled, we get a pair that consists of that point, and its true label, plus or minus, according to the target function. So let me give you a simple example. I mean, this is actually a real-world example, but it's simple in this, on the level that we'll talk about it now. So the example is sort of learning to identify pictures of faces. And then our input space is going to be a matrix, let's say k rows by l columns, of real numbers, where every real number represents a pixel. Okay, so maybe these numbers are in 0, 1, whatever, but the idea is every real number will represent the color of the pixel. And then this whole matrix gives us, the colors of different pixels in a picture of size k by l. Now, our target function is going to be label a point by plus if it's a face, if it's a picture of a face, and minus if it's not a picture of a face. So essentially what we have here is we're getting our data set, or training examples, or basically these pictures, accompanied by a label face or not face, plus or minus. And then our goal is to learn a function that when we see a new picture, we'll be able to classify it as a face or not a face, and we'll do it in a pretty accurate way. We'll talk in a minute about what I mean by accurately. Okay, but this is just sort of mapping the notations to this real-world example. So here's another example that is much more abstract, but I'll actually use it like as a running example for most of the lecture because it's sort of really easy to instantiate the definitions and some of the results for this example. So here, our input space, x, is going to be two-dimensional Euclidean space, so just the real plane, R2. And the function f is axis-aligned rectangles. So what do I mean by that? We have like the y-axis and the x-axis. And then we looked at rectangles whose edges are parallel to the axis. And the way we think about a rectangle, it's a function from the input space to plus or minus, where every point inside the rectangle, and let's say it's a closed set, so including on the boundary, is labeled plus, and every point outside the rectangle is labeled minus. Okay, so every rectangle like this can label points of our input space, and that's sort of the kind of function that we're trying to learn here. So based on a few examples, like here, maybe we don't know what the target is, but we'll get these positive examples, and we'll get these negative examples. And based on that, our goal is to return some rectangle that would have a high level of agreement with this target rectangle. Cool. So let's try to be a bit more formal about what we mean by sort of being, we want this process to be accurate. What do I mean by accuracy? And also think about, when we talk about probably, approximately, what these words mean. So we'll first define the error of a function, and this is relative to a distribution D and some target function f sub t. So the error of f is the probability that when we sample an input point according to D, f will disagree with the target on that point. Right? So it's the probability when we sample x according to D, that, actually I need to kick this x out here, that ftx disagrees with f of x. So let me just correct this for a minute. Okay. All right, so it's the probability that when we draw an x, x is such that the target function disagrees with the function f. So this is what we think of as the error of the function f. Now, in addition, so this is the approximately in probably approximately correct. And the idea is we're given some accuracy parameter, epsilon, and we would like to find the function f whose error, according to this definition, is at most epsilon. So this is what I mean by being accurate. However, there's also the probably thing. And this, the way to formalize it is that we have an additional parameter called the confidence parameter delta. And our goal is to achieve the following weird thing. We want to find a function that has error at most epsilon with probability at least 1 minus delta. Now, what's the deal with this delta? Like, why do we need this additional confidence parameter? So the idea is that we're going to have some randomness in the learning process. And specifically, the type of randomness we'll focus on today is the randomness in getting samples. So the point is, it could be the case that we got really unlucky, and we sampled IID according to D. IID is independently and identically distributed according to D. But we happened to sample the same point again and again and again and again. So, we took 1 million samples, we got incredibly unlucky, we just saw the same point again and again, right? So even though the number of samples is large, that's not a very useful data set. We just see one point and its label, even though we sampled many, many things. But intuitively, that's unlikely to happen, right, this extreme situation. So what Delta is trying to do is capture, to give us some slack in terms of, okay, you might get unlucky, and then your process will fail. But we want to say, at least with probability 1 minus delta, with pretty good probability, your process will succeed. That is, you won't get really unlucky in the sampling process. And then, if the process succeeds, then your accuracy should be pretty high.
So where is the randomness from the last?
So the right. So the error f is not really a random thing. It's according to a distribution, but there's no randomness. The randomness is that our learning algorithm will learn a function f based on random samples. So once you fixed f, there's no randomness. But the randomness is in learning f because of the samples. Okay, so are these definitions clear? Okay, this is really important stuff. Okay, so now we come to the first hellish definition of this lecture, the first one with many quantifiers, and that's a definition of a learning algorithm. So it's a long definition. I'm going to do this really slowly. So what's a learning algorithm? It's some function L that is a function from training examples to the function class f. So the idea is, it gets these training examples x1 to xm, and they're true labels. And it outputs a function in our target function class f. And it has to have the following property. For every epsilon and delta, so the game is you give me your desired confidence and your desired accuracy. And now I want to achieve the goal that we just specified on the previous slide. So for every epsilon and delta, there is some number, m star, that depends only on epsilon and delta. So you give me your epsilon delta. I tell you, okay, here is my number m star, based on on the epsilon delta that you told me. Now I'm going to draw m examples where m is at least m star. So I gave you some bound. Now you're going to give me examples, and the number is going to be at least this bound m star. So that's a lower bound on how many examples you have to give me. The beautiful thing here is this every d thing. So the position of this quantifier. So I want this process to work for any distribution d, and this m star is going to be independent of d. You as the adversary, you're sort of trying to mess with me. You can fix the distribution. You're not going to tell me what it is. And nevertheless, my m star is going to work for any distribution that you want. Okay, that's one of the really beautiful things about this definition and about the fact that it can be achieved. So I'm not going to know what the distribution d is, And moreover, my results are going to be completely independent of which distribution you choose in order to mess with me. So for every d, if you give me m examples d, drawn according to the fixed distribution d, then I apply my learning algorithm to the example z, I get a function f, and this function f achieves the goal that we talked about before. The probability that the error of f is at most epsilon is at least 1 minus delta. Okay, so like I said, this is confusing. Let's maybe stare at it for another 30 seconds.
Is there exist an m star, and then what's the parentheses around epsilon delta? Is that just m star and epsilon and delta?
No. So m star depends on epsilon and delta. So the game is you give me your desired accuracy and confidence, and then I tell you m star. And the definition is there has to be such an m star for every, so it's for all epsilon and delta exists m star, such that for all d, when we sample according to d, we get that kind of guarantee. Okay, so it's for all epsilon and delta exists m star, for all d, you get the guarantee. So 3 quantifiers, Ankush.
So the z is the set of examples, right?
Yes.
So maybe we should have that L is a function from sets of training examples to n, right? Not
Yeah, so L is a function from training examples, which is z, to f.
maybe it should be sets of training examples because
Oh, sure, okay, yeah, you're right. Okay, so L is really a function from sets of like any number of training examples to f.
and why do we have this condition that it should work for every distribution? Why can't we have a weaker definition where m star depends on d?
Because you can achieve even this kind of guarantee. So I mean, I guess like if it wasn't possible to achieve this kind of guarantee for like interesting function classes, of course there is some work that is also specific to distributions. In fact, sometimes you can't get this kind of guarantee, and then people ask, okay, can we get it for a specific distribution, like some kind of uniform distribution? But the beautiful thing is that we often can achieve this kind of guarantee for function classes that we care about, and then it's sort of a very agnostic definition where we say, okay, we don't need to assume anything about what d is. Nevertheless, we can make this kind of guarantee, especially if m star is going to be pretty small. Okay, so
but that's the thing. I mean, m star. So because m star should work for every distribution,
Sure.
it could be really high.
definitely, and it could be lower for some distribution. So, for example, if you take a distribution that is degenerate at one point,
Yeah,
right, just gives probability 1 to 1 point, that's going to be very easy. So for some distributions, it's going to be too easy. In some cases, there is some work talking about specific interesting distributions, but we'll focus on this because really we can get very nice results even in this very strong definition. Matthew?
I'm sorry if I missed it, but do the m examples need to be unique?
No, so the m examples are drawn from the distribution D. For example, D could be give probability 1 to a single point, so you'll definitely get all of the m examples on the same point. Or it could give like very high probability to some point. If it's like I mean, for some reasonable distributions and input spaces, it's very unlikely you'll get the exact same example twice, but it's definitely not part of the definition. D is some distribution, we could get the same examples. The only thing is you have to draw randomly every time according to the same D. So that's part of the issue of like, you could get unlucky and see the same examples again and again, or examples that are very close to each other, but we'll see that, that sort of doesn't happen, in a sense.
So the m examples can be the same, they just need to be randomly drawn.
Yes. Yeah. So we're drawing we're drawing with replacement, so we could get the same example. Yeah.
Are we still assuming target functions in big F?
Say again?
The target function?
Right, so the target function is in the class F. Okay, so we're going to assume that throughout the talk. The question was, is ft the target function in F? And the answer is yes for this talk. This is called proper learning. There's also some work when f of t is not in the function class F, but that's going to be our focus for this talk. Yeah.
Is there some way that you can have some bound on m star?
Yes, that's what we'll do on the next slide. Excellent. So the question was like, can we get a bound on m star? And really what we want is, this whole lecture will be about how to get bounds for m star. So if it was just there exists an m star, it wouldn't be very useful. Also going back to Ankush's question, if it's something huge, then we just said, okay, it exists, but we wanted this very strong guarantee for any distribution. We said you need a zillion examples. That's not going to be very helpful, but we'll see that actually we can get nice values of m star. Great, okay, so let me show you exactly such an example. We're going to do this in detail. So I'll get back to this very simple example of axis-aligned rectangles. We'll derive a specific value for m star, and then in the end, we'll see how we can get bounds for more useful function classes. So again, the input space is the plane. Our function class is these axis-aligned rectangles. And here's our learning algorithm L. We get a bunch of examples, and what we return is the rectangle that gives us the tightest fit around the positive examples. So it's going to exactly touch the positive examples at the boundary. It's going to be defined by these positive examples. And I want to argue that this is a learning algorithm for axis-aligned rectangles. And moreover, that it has the following, m star is often referred to as sample complexity. So it has the following sample complexity. For a given epsilon and delta, if you give me 4 over epsilon ln 4 over delta examples, then I'm going to learn a rectangle with error epsilon with probability at least 1 minus delta. Okay, so I'm going to achieve that goal if you give me this many examples. Michiel?
Do we have a condition on the distribution that there has to be a perfect rectangle that perfectly separates?
Yes. Yeah, so part of saying, I mean, part of saying like our target function is in the class basically means there is a rectangle that perfectly separates the positive from the negative examples in the real world, according to the, yeah. Right, so it's actually not an assumption about the distribution, it's an assumption about, you know, how points are labeled in the real world. So they're labeled by this rectangle that separates all of the positive examples from all of the negative examples. In particular, any distribution that you would give me, if it's inside this magic rectangle, you would get positive. If it's outside, you would get negative. Okay, so I want to prove this theorem. It's a non-trivial proof. I don't expect that everybody will be able to follow, but you know, hopefully, like if you lose me somewhere in the middle, the proof is in the slides. You'll be able to take another look at home. And also, I mean, it's really more about giving you an idea of like how one. I mean, right now it seems really mysterious, like how you would even go about proving something like that. So I just want to give you the important thing is to give you an idea of like how you would directly prove a theorem like this. You know, what are the even kind of arguments that we're trying to make? It will get like a bit hairy towards the end, but it's really about, you know, what are the arguments that one makes in order to prove something like that. So here's the proof. So we have a target rectangle R, which again is our target function. So it perfectly separates the positive examples from the negative examples in the world. And again, our learning algorithm returns the tightest fitting rectangle that we'll call R prime around the positive examples. So look at the illustration. We got, so we have 8 examples overall that we have in our training set in Z. 3 of them are positive, 5 are negative. Now this is the real rectangle, so notice that everything inside is positive, everything outside is negative. But what we do is we return the tightest fit around the positive examples. So that's the tightest fit. It's a different rectangle, R prime, and that's what our learning algorithm returns. Okay, and we want to argue that this is a pretty accurate estimate for the true rectangle R. So let's just introduce one notation. For a region E on the plane, for some set, let's denote by WE its weight. It's going to be the probability that when I draw some input point X according to D, it's going to fall inside the region E. Okay, so it's sort of its weight, its total probability according to the distribution D. Yeah?
What about a space, like from where the points are?
So the points are in R2 in the two-dimensional Euclidean space.
Okay. So just the weight of any bounded region is 0?
So it depends on the distribution.
Oh, okay. Yeah.
Okay, so, you know. Right. Okay. Right, so, good. Okay, so I want to argue that the error of R prime, remember what we care about is to bound the error of R output R prime. And what I want to argue is that the error of R prime is the weight of R minus R prime. Okay, so can anybody tell me why, just to make sure we're on the same page in terms of definitions? Yeah.
There are also points that R would say that qualify, but R prime would say.
Exactly. And remind me your name? Ashvil. Yeah, so Ashvil is saying, why? Because basically these are the points where R would say they're positive, but R prime would say they're negative. Everywhere else, R and R prime agree. So outside of R, both R and R prime say negative. Inside of R prime, both R and R prime say positive. So the only place where they disagree, and I might have an error, is this region between R and R prime. Right? Because of course R prime is contained in R, right? That's clear. So that's the only region where we might make a mistake. And what we're doing is trying to bound the weight of this region, the probability that when I draw an example from D, it's going to fall into this problematic region. Okay, so next, what I'll do, so we're only interested in R minus R prime. Let's focus on this region. I'm going to divide it into 4 strips, T1 prime to T4 prime, where T1 prime is the strip between the top of R and the top of R prime. T3 prime is the region between the bottom of R and the bottom of R prime, and then you have one to the right and one to the left. So these are the 4 strips, T1 prime, T2 prime, T3 prime, and T4 prime.
They intersect, right?
They intersect, yes, and that's exactly why we got the next point, which is the error of R prime is at most the sum from I equals 1 to 4 of the weight of Ti prime. And the idea is, we said the error of R is the total weight, the error of R prime is the weight of the region R minus R prime, which consists of the 4 strips. Like Dimitri said, they intersect, but we still get this upper bound, right? So we have, there are some intersections, we're double counting, but definitely the weight of R minus R prime, which we said equals to the error of R prime, is at most the sum of weights of these 4 regions. Okay, it would usually be less because of the intersections, but we can get this inequality. Excellent. So what we'll do is we will estimate the probability that for some I, the weight of Ti prime is at least epsilon over 4. Why are we interested in this? So the way to think about it is if each of these strips has weight less than epsilon over 4, then all of them together will have weight less than epsilon, which is what we want. Okay, so the bad event that we care about, we're actually going to be generous and say, okay, we're going to give up, we're going to have a bad event if any one of these strips has weight at least epsilon over 4. Okay? And we're going to try to estimate the probability of this bad event happening. So this is sort of, I think here you're starting to get an idea of where this epsilon delta thing is coming from, right? So now we're talking about the probability that a weight of a region is at least something, where the weight is related to the accuracy, to epsilon, and this probability will be related to delta, to our confidence parameter. Okay, so let's focus without loss of generality on the strip T1 prime. Okay, we're going to just think about one of the strips, let's say T1 prime. And what we'll do is we'll define another strip, T1. And the way we'll define it is, we're going to start at the top of R, and then we're going to sort of take a rectangle, and we want the weight of this rectangle to be exactly epsilon over 4. So we're going to take the boundary of this rectangle, the bottom boundary, and push it downwards until we hit total weight exactly epsilon over 4. That's our definition of T1. Okay? Good question. So Alex is saying, why does it exist? So notice that if R has weight less than epsilon, then the whole thing is obvious, right? Because we're saying the only thing we care about is the weight of R minus R prime. If all of R has weight less than epsilon, then there's no problem. Therefore, R, we can assume, has weight at least epsilon, and then if we push from the top boundary down enough, we'll hit epsilon over 4. Oh, you're saying because of discreteness of the distribution?
I mean, it doesn't matter, I think.
Yeah, I mean, if it's discrete, let's say the first point where it's, let's not get into it, but it would be like the first point where it's less than epsilon over 4. Good. But it's a subtle and good point. Okay, good. So, so now I want to make, yeah.
Are we assuming that R prime is containing R?
Say again?
Are we assuming that R prime is containing R?
We don't need to assume that. What we've assumed is that R is like the truth, right? The true labeling. And we defined R prime to be the tightest fit around the positive examples. Okay? Now, every positive example is contained within R. So definitely like the tightest fit around the positive examples is going to be contained within R. So it's a really good point, but we actually don't need to have an additional assumption. It just follows from our assumption that R is the truth, right? That all of the examples are going to be consistent with R. So if we take, like, for example, if we took the tightest fit around the negative examples, or like just outside, then we wouldn't have this property. But because we took the tightest fit around the positive examples, then we do have this property. Yeah? Good. These are great questions. Okay. So I want to argue that a couple of properties hold. The first property is that the weight of T1 prime is at least epsilon over 4, if and only if T1 is contained in T1 prime. Now, the way to think about it is, both T1 and T1 prime are sort of strips that start at the top edge of R. Now, if T1 prime is more than epsilon over 4, right? So basically, T1 stopped at the epsilon over 4 point. T1 prime, if its total weight is more than epsilon over 4, right? Its bottom edge has to be below the bottom edge that defined epsilon over 4 weight. On the other hand, if it's less, if T1 prime is less than epsilon over 4, then basically this edge is at the epsilon over 4 point. This edge has to be somewhere here. It's going to stop before we hit the epsilon over 4 mark. So we have this property by the definitions. Now here's a slightly more subtle point. We're actually now at the most hairy part of the proof. It's going to be pretty easy from this point on. But the second point is that T1 is contained in T1 prime, if and only if all of our input points that we sampled, x1 to xm, are not contained in T1. So the way to think about this is, suppose that we had some input point inside T1. Then it's definitely a positive point because it's inside R. And then, when we take the tightest fit around the positive point, it's going to stretch all the way up to this point, to where this example is. And then, this top strip will be smaller, will not be contained in T1. Right, so again, if we had the positive example here, R prime would stretch all the way up here, and then, T1 prime will only be this. It won't be contained in T1. On the other hand, if all of our samples are outside of T1, so all of the positive examples are here, when we take the tightest fit, its top boundary is over here, and then when we define T1 prime, it's going to be defined by those samples and below T1. Class? I can't hear you.
Are we assuming that rectangles are open?
No, they're closed.
Can we not have a case then where there's a sample point on the boundary of T1 that's also on the boundary of R prime? And so the last intermediate question
So you're talking about just like this boundary issue? Yeah, yeah, I think it's going back to Alex's point. Yeah, we can definitely deal with those. So let's say, I guess this is sort of implicitly assuming a distribution with measure 0 on every point. If there are, if the distribution is atoms, I guess we need to be a bit more careful. These are good points. Okay, good. So everybody agrees with this up to like some very small subtleties? Good. So if we believe these 2 points, so we have this if and only if this if and only if this, we just get that the weight of T1 prime is at least epsilon over 4, if and only if all of the points are outside of T1. So remember, this is the bad event that we were worried about. So so what we want is to estimate this probability, and now we have a good way of estimating it. All we need to ask ourselves is what's the probability that all of our samples end up outside of T1? And this is really easy, right? Because we define T1 in a very specific way. It's a region with weight epsilon over 4. So the claim is the probability that all of these points are outside of T1 is exactly 1 minus epsilon over 4 to the power of m. Because, the probability of any point falling in that region is epsilon over 4. The probability of any single point falling outside of the region is 1 minus epsilon over 4. And then you need that to happen for all m points again and again. So it's 1 minus epsilon over 4 to the power of m. Okay? So this is, I think this is actually really cool, right? Because finally, we sort of see how this whole thing connects to probabilities, to the probability that our process will actually work out and will get the desired outcome with the desired confidence. Okay, we're not there yet, but this sort of makes the connection. So let's finish the proof. So what we're saying now, going back to the beginning of the proof, we said, well, the probability that our error is at most epsilon, we said we just need to worry about the region r minus r prime. And then we said, well, this will definitely happen if each one of these strips, ti prime, its weight is less than epsilon over 4. Each one of these bad events, we said, happens with this probability. Then by the union bound, none of these 4 bad events would happen with probability 4 times 1 minus epsilon over 4 to the power of m. So that's an upper bound on the probability of any of these 4 events, bad events happening. Okay, so we said before, okay, they have intersections. We were generous in several ways. We said, okay, we don't care about intersections. We're taking the union bound. But this definitely gives us an upper bound on the probability of the bad event that we're afraid of. Okay, so what we want is if, with this probability, the adversary successfully messed up with us and we got bad examples where we didn't see some crucial regions and we made a big error. But with this probability, we can guarantee everything worked out. And all we need now is to say this probability has to be at most the given delta, right? Because we said we want to mess up with probability at most delta. So take this is smaller or equal than delta. Then you extract m from this inequality, and you get the bound that we specified in the theorem formulation. Okay. Cool. So up to like a few subtle points that I should think about offline later, but I guess there was maybe some implicit assumption. Hopefully the proof is more or less clear. And again, like what I really want you to take away is the intuitions of how we even go about connecting accuracy and confidence. Cool. Okay, so that's the first part of the lecture. Now we're going to talk about, there's going to be a second part, which initially will be almost disjoint from the first part. And then at the end, we'll see how the first part and the second part connect. But I'm saying this because if you lost me in the last few slides, you can completely forget for now about all of the stuff we said so far. And now we're starting over with like new definitions and new results. Okay? Cool. So, the last result we talked about gave us a specific sample complexity result for this for learning axis-aligned rectangles. And what we're going to try to do now is build a theory that will give us more general results. So let's again have some sample, some training set, some set of examples x1 to xm. And the first definition is already a bit confusing. I'm going to define the following strange set. The set is pi sub f of s. So it depends on s, and it depends on a function class f. Now, how do I define it? This is the set of vectors where the vectors are, you take some function in f, and you apply it to every point in the set s. On every point, the function gives plus, minus, minus, plus. It gives some label plus or minus. And then what we're doing is we're looking at the set of all of the vectors that are achieved in this way. Okay? So we take, function number 1 in f, and we say apply it to every point. We get a vector of pluses and minuses. We take function number 2, we apply it to the training set. We get a vector of pluses and minuses. All of these vectors together make up the set pi sub f s. Now notice that we can apply 2 different functions to all of the examples and get the exact same vector. So it's not that the size of this set is equal to the size of the function class f. It's some set, and we could have multiplicities in terms of like we apply f 2 different functions, we get the same vector. So let me show you an example. So again, our favorite axis-aligned rectangles example. Our set S is going to consist of 3 points on the plane, so it's these 3 points. And what I'm going to do is, I want to compute the set pi fs. And I want to argue that the set will contain all possible 8 labelings of the 3 points by pluses and minuses. Okay, so notice that for 3 points, the maximum size of the set is 8. Because it's just like the set is a vector of pluses and minuses. For each of the 3 points, either plus or minus. So it can't be more than 8. And I want to convince you that the set will actually contain all 8 vectors of labelings for these points. So, if we want to label all 3 points by minus, we just take a rectangle that's outside all 3 points. If we want to label any one of these 3 points as plus and the other 2 as minus, we can take, this rectangle, or this rectangle. So this gives us these 3 vectors of labels. If we want to label 2 points as plus and the other point as minus, we can take this rectangle, this one, or this one. So this gives us these 3 vectors of pluses and minuses. And finally, if we want to label all 3 points as plus, take a rectangle that contains all of them. Okay? So our set consists of all possible vectors of length 3 of pluses and minuses. Now notice that, if I wanted to get this labeling, I could also take a much bigger rectangle. That would also work. So these 2 different functions actually give me the same labeling. But the important point is, I can construct every possible labeling with my function class on this set of examples. Is everybody okay with this definition and example? Matthew.
So then the size of pi f would be 2 to the n.
At most 2 to the m.
Yeah.
Okay, so in this case it's 2 to the m, but really it can be at most 2 to the m. Okay, so let's take a break at this point and practice the definitions. So I want to practice it on a slightly simpler function class. So now x, our input space, is going to be the real line. Instead of the plane, it's just going to be the real line. And the function class is the set of intervals. So it's really like rectangles in 1 dimension. So we say every function is an interval, where the points inside the interval are labeled by plus, and the points outside the interval are labeled by minus. Okay, and it can be any interval. Every interval defines a classifier on the real line. Now, imagine that I take my set S as just 2 different points on the line. It doesn't matter which ones. Let's say 0 and 1. So that's the set S. And my question to you is, what is the size of the set pi f of S? So that's poll number 1 on Piazza. Okay, excellent. So we have a 2/3 majority for the right answer, which is 4. Right? So, and the reason is, would somebody like to say what the reason is? So why is it 4? Ankush?
So you can take an interval which does not include any of the points, then you can include one, then you can include the second.
Exactly. Right. So Ankush is saying, for each labeling that you want, you want a plus and a minus. Take an interval that includes 1 point and not the other. You want a minus and a plus. Minus, minus. Take an interval outside. Plus, plus. Take an interval that contains both. You can get all 4 possible labelings.
So because there's 2 points, it's just 2 to the n.
In this case, but that leads us directly to the next poll. So now there's going to be 3 points. Okay. So next poll. Same thing, but instead of 2 points, we have 3 points. What is pi fs? Okay, I sort of gave it away here that I added more options in the poll on Piazza, but there are fewer options here, so it's probably one of these options. Okay, 10 more seconds. Excellent. Okay, so we have a slight majority for the right answer, which is 7. So can somebody tell me what the labeling that we can't achieve is? Over there? Excellent. And what's your name? Jatik. Right, so Jatik is saying, what's the labeling that we can't achieve? Take off the 3 points, 2 pluses at the ends, and minus in the middle. Right, so we have something like plus, minus, plus. And then if we have an interval that contains the 2 pluses, it will have to contain the middle point as well and label it by minus. So we can never label the 2 outer points by plus and the middle point by minus. But every other labeling, it's pretty easy to check, you can actually achieve with one interval. Okay, so we can achieve each one of the 8 labelings except for this problematic one, and therefore the size of the set is 7. So this goes back to like a couple of questions. It shows that the size of the set is not always 2 to the m. Here there's actually a labeling that we can't achieve. Great, okay, so now we get to the second very complicated or very hard to digest definition of this lecture, the definition of VC dimension. So first of all, we're going to say that a set S is shattered by a function class f. Very cool terminology for this. If the size of the set, sort of the math definition sounds much less exciting than the verbal definition. So if the size of the set pi fs is 2 to the size of s, or in other words, if we had m examples, if we could actually achieve every possible labeling over these points, which means the size of the set is 2 to the m, or 2 to the size of s, then we say that the set S is shattered by f. Right, so for example, in the examples that we saw, the function class intervals shattered the set that consisted of 2 points, but wasn't able to shatter the S that consists of 3 points, because we couldn't get every possible labeling. Now, what's the VC dimension? The VC dimension of a function class f is the cardinality of the largest set that is shattered by f. So there are many quantifiers here that we rolled into the definition of shattered. Okay, but basically, let's think about it for a bit. Right, so what we're saying is, let me tell you like how you would prove a lower bound on the VC dimension, and you'll tell me how to prove an upper bound. So to prove a lower bound, we would need to prove that we would need to show some set S of size D. So we want to show that the VC dimension is at least D. So we need to produce one set of size D such that it is shattered by F. Or in other words, such that for every possible labeling, there is a function in F that would give you that labeling. So there are 3 quantifiers here, okay? So it says the VC dimension is at least D if there exists a set S of size D, such that for any labeling of S, there exists a function in F that gives you that labeling. So we rolled the 2 latter quantifiers into the definition of shattering. Okay? So now how do you prove an upper bound? How do you prove that the VC dimension is at most D? Okay, so it's a logic exercise with quantifiers. Yeah?
For every set of size D or larger, we have to show that F cannot shatter.
D or larger? Almost?
All D, just D.
Okay, so larger than D, right? So, right. So exactly. So we want to show that F can shatter that set, which means there exists a labeling. So let's make it explicit. Okay. So what we need to show is that for every set of size D plus 1, there exists a labeling. You know, what does it mean it can't be shattered? There exists a labeling such that no function in f can achieve that labeling. Okay? So again, to prove that the VC dimension is at least d, you need to give one set of size d, such that for every labeling, there exists a function that gives you that labeling. To prove that it's at most d, you have to show that for every set of size d plus 1, there exists a labeling such that no function in f gives you that labeling. So you guys will practice this in the homework and maybe on the midterm. But this is like a definition that's very hard to digest. But you'll see, I mean, when we talk about applications, it's really one of the most beautiful definitions that I've ever seen in computer science. I mean, we'll see in a minute like the connection between this definition and like sample complexity. But it's really something that like on a very deep level captures the combinatorial richness of a function class. And it's like really powerful, like the fact that you can do this formally and what it gives you in terms of how difficult it is to learn a function class. Okay? So even if you didn't digest it now, you really should spend the effort later because it's a really, really beautiful and very, very deep concept. By the way, VC are Vapnik and Chervoninkis. Okay, so let me give you an example of VC dimension for our favorite set of axis-aligned rectangles. So I want to argue that the VC dimension of this class that we've been talking about all along is 4. So to do this, I first need to give you an example of 4 points that can be shattered by axis-aligned rectangles. So here's 4 points like this. Right, so, you know, give me some labeling, like if you want plus, plus, minus, minus, I'll give you this rectangle. If you want to do plus, 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 minus, I'll give you this rectangle. It's very obvious that like for any labeling of pluses and minuses, there's some rectangle that would give you exactly that labeling. Okay? So this is a set that can be shattered by axis-aligned rectangles. On the other hand, and I don't want to be formal about this, but for every 5 points that you take, so I want to show that the VC dimension is exactly 4. I need to prove an upper bound of 4. So that will entail proving that for every 5 points, there's some labeling that can't be achieved by f. And that's true because for every 5 points on the plane, there's one that is internal to the others. It's in the convex hull. And that means that if you take a rectangle that labels the outer points by plus, the inner point would be minus. So it's the same thing that like we saw for intervals on the line. You know, plus, plus on the sides is minus. You can't get plus, plus and minus in the middle. This is the same thing, but on the plane. When you go up to 5 points, to capture all of the outer points, you would have to label the inner point by plus as well. Alex?
You have just a 5 cone in a convex, like 5 points in a convex
Yeah.
position.
Right, so like a pentagon, basically.
Yeah, like
yeah. So the thing is, so if you have something like this, well, it's going to be butchering a pentagon, but then basically, if you want to label this is plus and this is plus, you'll have to label this is plus as well, because it's axis aligned. Oh, so right. Yeah. So if
it depends on where that.
So if this is parallel to the x-axis, then yes. If not, then there'll definitely be an internal point. Okay. Good. Okay. So good. So we just proved that the VC dimension is 4. Right. So we showed an example of size 4 that can be shattered, and we proved that no example of size 5 can be shattered. So there will be some labeling that can't be achieved. Good, so let's continue practicing. So we'll go back to our simple example of intervals on a line. Let me actually hide poll number 4 for now. Well, anyway, ignore poll number 4 for now. So we have x is the real line, f is intervals like before. And the question is, what is VC dimension of f? 1, 2, 3, or none of the above? That's poll number 3. Okay, excellent. You guys are really paying attention. So 84% for the right answer, which is 2. And like I said, we basically already solved this because we saw an example of size 2 that was shattered, like the previous 2 polls. we gave an example of size 2 that was shattered by intervals. And then we gave an example, it's really a general example, of 3 points that we saw can't be shattered. And of course, we didn't make any assumption about these 3 points, which was just a general result about any 3 points. Right? So this is exactly the definition of showing that the VC dimension is exactly 2. Yeah.
There's some generality for some dimension of Euclidean space for what the dimension of the VC space is.
So some generalization of like rectangles.
Yeah.
So
I guess this is
yeah, I mean you can think about boxes like in 3 dimensions and so on. Yeah, I mean it's you can naturally make that generalization. I don't know what the VC dimension higher dimensions is. However, we'll see. So on the next slide, we'll see linear separators where we'll really argue about the general case. So that will give you like a partial answer.
I think it's 2D for boxes.
So I'm not sure like what happens with this like the upper bound that we just gave in 2 dimensions, like what happens in higher dimensions. Like for a fact that it's 2D? Okay, so Ritesh has seen in the past that it's 2D for boxes in higher dimensions. 2 to the D, right? 2D you said. 2D, really? Oh, okay, interesting. We'll take your word for it.
Then 4, then so 6.
Yeah.
Yes.
Okay, cool. Priya?
So far, like in the previous slide, you proved, you gave a set of size d plus 1 that could not be shattered. And because we're in R2, right, any set that's larger, you can, argue about a subset of it.
Mm-hmm.
But have we made any assumptions that allow us to always, in general, just give an example of d plus 1? Or are there times when we would actually have to, like, do something to prove for all sizes greater than d?
Yeah, so I mean, if I understand your question correctly, like in the case of the function class being intervals, it's sort of obvious that like if you take any 2 points, there's nothing special about the argument, or sorry, any 3 points, there's nothing special about the argument that we use to say that it can't be shattered. But in general, for other function classes, like you will have to be more specific, right? So it's the different examples do have like different characteristics. It really depends on the function class. So this was like a very, very simple, it's a very simple function class, and therefore the proof is relatively simple. I guess, yeah, so right, we're going to talk about linear separators. We'll just do the lower bound proof for linear separators, but there the upper bound proof actually requires more careful arguments. So already there, it gets a bit trickier. Okay, so last poll question for today. So now instead of just intervals, I'm going to take my function class f to be unions of intervals. What I mean by this is you can take any number of intervals, you take their union, and then everything inside any of these intervals, you can take as many as you want, let's say a finite number. Anything inside the union is labeled by plus, and everything outside this union, outside any of the intervals, is labeled by minus. So that's also a legitimate function class, right? And the question is, what's the VC dimension of this function class? Is it 2, 3, 4, or none of the above?
Any number of...
Any finite number of intervals, yeah. Okay. Excellent. You guys are great. Okay, so why is it possible to shatter? I guess the argument would be we can shatter an example of any size, a set of any size. Why is that true?
Can you just draw individual intervals around each?
Perfect. Right. So we can just like for any positive example, just take like an individual interval just around that positive example. That would give you exactly the desired labeling. Okay, so this means we can shatter any size of S. Great. Okay, so we're almost done. So the last thing I want to show you, we talked about these axis-aligned rectangles for most of the lecture. I want to connect this whole thing to a more useful function class, the class of linear separators. Zico talked about this a bit in the last lecture. It's something people really care about, like in the breast cancer example, so classification by some linear separator, by a hyperplane. So let's think about this class a bit and about its VC dimension. So now we have d-dimensional Euclidean space. We're working in the general case. And we define a linear separator, like Zico did last time, as a function that takes as input a vector of dimension d in Rd. And so what it does is it's defined by a vector of parameters a, so it's also a vector of length d, and by some real number b. And then what it does is it takes the dot product of a and the given x, adds b, and then takes the sign of this, and let's say if this is greater or equal than 0, then we label by plus. If it's smaller than 0, then we label by minus. Okay? So that's a linear separator. And a theorem about linear separators is that their VC dimension is d plus 1 in d-dimensional space. So what I want to prove to you is just the lower bound. The upper bound is slightly trickier. We'll maybe do it as a homework problem. But let's prove the lower bound. So to prove the lower bound, what we need to show is a set of size d plus 1 that is shattered by this function class of linear separators. So I just need to define one set. And maybe this will also be a nice example of how it really has to be a specific set. So it's not that every set can be shattered, but I'm going to define a specific set that can be shattered. So how will I do that? Let's just for notation denote the ith unit vector by ei. So this is the vector of length d that is all zeros except for a 1 in the ith coordinate, sorry. Right, so the first unit vector is 1 and zeros, the second is 0, 1, zeros, and so on. And the way I'll define my set is it's going to consist of each one of these d unit vectors plus the all 0 vector. Okay, so it's either all 0 or these vectors that have 1 in coordinate I and everything else is 0. So I want to try to shatter this set S with my function class of linear separators. And here's how I'm going to do it. So now the game is you give me a labeling and I try to achieve that labeling. Let's represent the labeling that you give me by a vector or by d plus 1 numbers y0 to yd. So y0 is the label that you want this thing to have, the all 0 vector. And yi for I greater than 0 is the vector that you want ei to have, the ith unit vector. So basically, if you tell me 1, it means you want the label to be positive. If you tell me minus 1, you want the label of the corresponding point to be negative. Right, so that's how you specify your labeling. And now I want to come up with the parameters a and b of my linear classifier that would exactly achieve the labeling that you chose. So what I'll do is, as my vector a, I'll take the vector y1 to yd. And as b, I'll take y0 divided by 2. Okay, so let's see why this works. So first of all, let's look at this point, at the all 0 vector, and let's make sure that it has the right label. So the all 0 vector, I multiply a by the all 0 vector, I get 0. And then I add b. So when I add b, what I get is just y0 divided by 2. So basically, this will have the same sign as y0. Right? The divide by 2 doesn't really matter. So the sign of this will be the same sign as y0. And that means I'm OK on that example. Now, what about all of these guys, all of the ith unit vectors? So when I multiply a by the ith unit vector, what I have left is yi. Right? All of the others will be multiplied by 0. The only one that gets multiplied by 1 is yi. So the result of this is yi. And then I add y0 divided by 2. Now I claim that this will have the same sign as yi, right? Because yi is either minus 1 or 1. y0 divided by 2 is either minus 1/2 or plus 1/2. But then, whatever you get, it's going to be the same sign as yi because the second thing is smaller in absolute value. So this thing will again have the same sign as yi, which is what I'm trying to achieve. Okay? Yeah, sure. From the beginning?
No, the yi.
Oh, for yi, okay. So for yi, what I get is if you take this vector a and you multiply it by the ith unit vector, right? So what we get is, so you basically get So we got 1 times y1, 0 times y0 plus y1 plus 0 times y2. And then we have 1 times yi, and all of the rest are zeros as well. So the only thing that's remaining is this yi. Right, so from this dot product, we get yi. B is just y0 divided by 2. So yi is either 1 or minus 1. y0 divided by 2 is minus 1/2 or plus 1/2. But
Sign doesn't change.
so the sign doesn't change because it's smaller in absolute value. Okay? So again, like the sign will be the same as yi, which is what we want. Okay, so is everybody okay with this lower bound proof? So what we're able to do is give, a specific example that can be shattered by our function class of linear separators. Excellent. Okay, so yeah, in the upper bound, maybe we'll give it as a homework problem, but definitely don't look it up online. Great, so like I said, we had this first part of the talk when we talked about sample complexity. We talked about, PAC model, what the learning algorithm is. We gave a specific theorem for axis-aligned rectangles. Then in the second part of the talk, I switched gears and talked about VC dimension. But we actually, in the second part, since starting to talk about pi-fs, VC dimension, and so on, we didn't actually talk about how this is related to sample complexity. So this slide is where we actually make the connection between VC dimension and sample complexity and sort of understand why we were talking about all of this stuff. So first of all, let's just define that if for any k, there is a sample of size k that can be shattered by f, then we say that the VC dimension of f is infinity. Okay, so we said, the VC dimension is the maximum size of s that can be shattered. If there's no upper bound, we say infinity. So we saw, for example, that unions of intervals have a finite VC dimension. We can shatter a sample of any size. So the first theorem says that if a function class f has infinite VC dimension, it is not PAC learnable. Okay, so if you go back to the definition, it was this thing that said, if you give me epsilon and delta, there exists some m star. So this says there does not exist an m star no matter how large you want to go. Okay, I can always come up with some distribution that will really mess you up. So, so something like any union of intervals, that can't be learned in this model according to the strong definition of working for any distribution. On the other hand, if the VC dimension is finite, there's a very strong connection between VC dimension and sample complexity. And let me just point out that VC dimension is finite is very different from the function class being of finite size. Right? We talked about, rectangles and so on. These are infinite function classes. And this is, again, what's beautiful about VC dimension. The function classes are very large, but it really captures, the richness of the class. And it can say, even though your class looks huge, it's actually very limited in terms of what it can achieve. Right? So that's an important distinction. So this is saying if the VC dimension is finite, and let's call it D, and let's look at an algorithm. This is, again, a very interesting point. Let's look at some algorithm that all it does is it takes a set S, and it produces a function in f that is consistent with S, in the sense that it just labels all of the positive points in S as positive, and all of the negative points in S as negative. Such a function exists because we are in this realizable case where our target function is in the function class. Okay? So this is saying, all your learning algorithm has to do is to produce some function that is consistent with the examples that you saw. And if you do that, then L is actually a learning algorithm according to the definition that we saw. And moreover, its sample complexity, the value of m star, depending on epsilon and delta, is O of 1 over epsilon log 1 over delta plus D over epsilon log of 1 over epsilon. So really, one thing to note here is that this is linear in D. Okay, D appears here. And it's sort of linear in 1 over epsilon and logarithmic in 1 over delta. But the dependence on D, on the VC dimension, is really good. It's a linear dependence on the VC dimension. Yeah, Matthew?
That would explain why Cox is 2D and not 2D.
So why, So we don't, I mean, so we just proved the result about two-dimensional boxes.
Or I mean, multi-dimensional boxes, why,
Right, so if the theorem that we proved initially worked for d-dimensional boxes, then it would say that essentially. But that theorem was very specific to like two-dimensional boxes. I mean, you could prove such a theorem for d-dimensional boxes, but at least like I don't think it follows from what we proved.
All right, I don't mean like it actually proves it, I just mean it's more like it relates.
Sure, so you're saying like we could generalize that proof in a way that would imply this bound. Perhaps. Good. Okay. So, but really, what I want to point out is that the dependence on D is linear. So it's great dependence on the VC dimension, and again, linear dependence on 1 over epsilon, logarithmic dependence on 1 over delta. So if you can get very high confidence cheaply, it's a bit more expensive to get high accuracy in this bound. Yeah, I guess another thing to note, like if you want to think about boxes. So we said, at least in 2 dimensions, right, the VC dimension of boxes is 4, and then the bound that we proved essentially coincides with this bound. If you replace D by 4, and you get this O thing hide some constants, you basically get this bound. So the bound that we proved is pretty tight, or this bound for that class is pretty tight. Great. So. Yeah, maybe before I move on, let me just say again, this is just a really exciting theorem, right? So it just says we really captured something very fundamental about the function class, which directly translates to a connection to the sample complexity. Okay, so I want to just spend the last 3 minutes thinking a bit about real-world implications of this stuff, maybe trying to connect a bit to the previous lecture. So first of all, for linear classifiers, right, so what we said is the VC dimension of linear classifiers is D plus 1. So this would imply, with the theorem that we just proved, this would imply that learning linear classifiers is really easy. We just need to take something that's consistent with our sample, and then everything is great, right? We need like low sample complexity, and everything will be perfect. This sort of seems to contradict, some stuff that Zico's mentioning, that actually there are many approaches to doing linear classification, SVM, many other things, all of these loss functions. So why have people worked so hard? I mean, the reason is that we really made many simplifying assumptions, or a few simplifying assumptions today. One of them was that we were in this realizable case where things are perfectly separable, and that makes things a lot easier. So in particular, if you want to find a linear classifier that is consistent with your examples, and there is something that's consistent, this is just a linear program. So you just need the feasibility program that says for each of the examples, we need to satisfy this linear inequality. So that's really easy. On the other hand, if there's nothing that is consistent, and you want to minimize the number of mistakes, that's an NP-hard problem, as Zico mentioned last time. So from a computational complexity viewpoint, it gets a lot harder when you don't live in this nice world where things are perfectly separable. And if you look at this breast cancer data set, you can immediately see it can't be perfectly separated. So in the real world, things are trickier in that sense. Another thing to note is if you think about overfitting, so again, Zico spent half an hour talking about overfitting, and things like if we take a 50th degree polynomial, it could look really great, fit our examples really well, but generalize really badly. And the theorem we just stated said, all you need to do is be consistent on your examples. So again, this would seem to be a contradiction, but one reason for this is that we're assuming that our target function is in our function class. Right, so what this would be saying in the 50th degree polynomial world is that the data was actually, like the real world is actually labeled by a 50th degree polynomial, and we're trying to learn a 50th degree polynomial, and then really, what you need to do is fit your examples as well as possible by a 50th degree polynomial, and you'll do really well. The problem is that in the real world, the data wasn't actually generated by a 50th degree polynomial, so then if you try to fit it with something from that class, it would overfit. Okay, so that's the big difference, is that in the real world, the labels weren't nicely generated by some function that is in the function class that we're learning, right? And that's a really fundamental difference. So there are results about this kind of improper learning and so on, but just in terms of if you're wondering why this result doesn't directly contradict real-world stuff that Zico was talking about last time, the reason is that we were in this more simplistic model, and if you want to learn about how the theory extends to those kinds of settings, I guess you'd have to take a more advanced learning theory class. That's it for today.